The universe holds secrets, places where the rules we know simply cease to apply. Imagine a point where space itself collapses into an infinite abyss, where time stretches and distorts beyond comprehension. This is a place where nothing, not even the fastest thing in the universe can escape. We call them black holes, but that name, while evocative, is dangerously incomplete, because black holes are not empty voids. They are not holes, they are destinations. They are the final stop, the ultimate point of no return. So, what exactly is a black hole? It's what happens when gravity wins its eternal war against all other forces. Think of a massive star, many times the size of our sun, reaching the end of its life. Its fuel runs out, and the outward push that held it together for billions of years vanishes. Gravity takes over, crushing the star's core with unimaginable force. The matter is squeezed into a point so small and so dense that it breaks the very fabric of spacetime. At this moment, the universe draws a line in the cosmic sand. We call it the event horizon. It isn't a physical barrier you could touch, but rather a threshold. Once you cross it, return is impossible. The escape velocity, the speed needed to break free from the gravitational pull, becomes greater than the speed of light. And since nothing can travel faster than light, nothing can get out. One of the most mind-bending consequences of this extreme gravity is its effect on time. This is where reality splits into two different stories. For someone watching from a safe distance, an object falling into a black hole would appear to slow down as it approaches the event horizon. It would seem to freeze, its light stretching and reddening, until it fades away over an infinite amount of time. It would never actually seem to cross the boundary. But for the object itself, or an astronaut unfortunate enough to be on that journey, the experience would be completely different. Their clock would tick normally. They would cross the event horizon in a finite amount of time, perhaps just seconds, and continue their fall towards the center, where they would be torn apart by tidal forces and crushed into the singularity. Two different realities, both equally correct according to the laws of physics. This isn't science fiction. This is Albert Einstein's general theory of relativity at its most extreme. Einstein himself predicted the possibility of these cosmic monsters back in 1915. His equations showed that mass could warp spacetime, and a massive enough object could warp it so much that it created a hole. But he didn't like the idea. He thought that in the real world, some law of nature would step in to prevent such a bizarre object from forming. He was a genius, but on this point, the universe disagreed with him. For decades, black holes remained purely theoretical, mathematical ghosts. We couldn't see them directly because, by definition, they emit no light. So how did we finally prove they were real? How do you photograph the invisible? The answer was revolutionary. Scientists linked telescopes across the entire globe, creating a virtual telescope the size of our planet, the Event Horizon Telescope. Even with this incredible instrument, they didn't take a picture of the black hole itself. Instead, they captured its shadow. They photographed the silhouette of the event horizon, outlined by the superheated gas, dust, and light swirling around it just before being devoured. It was a ring of fire surrounding a perfect circle of absolute darkness, the first direct visual evidence of a black hole's existence. We've learned that black holes come in different sizes. There are stellar mass black holes, just a few times the mass of our sun, scattered throughout galaxies. Then there are the supermassive black holes, monsters that are millions or even billions of times the mass of our sun. We now believe that one of these behemoths lurks at the center of almost every large galaxy, including our very own, the Milky Way. Our galactic center is home to Sagittarius Asterisk, a supermassive black hole 4 million times the mass of the sun. With a reputation like this, it's easy to think of black holes as cosmic vacuum cleaners, relentlessly sucking up everything in the universe. But that's not quite right. Their gravitational pull is strong, but it follows the same rules as any other object. If you replaced our sun with a black hole of the same mass, Earth and the other planets would continue to orbit it just as they do now. We wouldn't be suddenly pulled in. You have to get very, very close to be in danger. However, on a galactic scale, they are architects. Their immense gravity shapes the structure of galaxies, their energy output can regulate the birth of new stars, and their interactions can sculpt the cosmos. They destroy locally, but they help organize globally. So, what lies inside? What happens after you cross the event horizon? This is where our current understanding of physics completely breaks down. Our theories point to a singularity, a point of infinite density and zero volume where the laws of space and time, as we know them, cease to exist. Is it a gateway to another universe? Is it a point of pure nothingness? The honest answer is, we don't know. And that admission might be one of the most important principles in all of science, knowing the limits of our knowledge. In the end, black holes are not just cosmic monsters, they are mirrors. They reflect the boundaries of our understanding, showing us just how much of the universe remains a profound and beautiful mystery. They are a reminder that the deepest truths are often found in the darkest places, and the closer we look into that darkness, the more it seems to look back at us, challenging us to keep exploring, to keep questioning, and to never stop wondering. Thanks for watching.